Hello, welcome to the video of session 8 of module 2 fast Fourier transform algorithm of the subject digital signal processing prescribed for 5th semester electronics and communication engineering students. Now, first let us have the learning objectives of this session. Here, first we will be considering finding inverse DFT using Radix2 FFT algorithm. Next, we will going into converting DIT-FFT algorithm for finding DFT to DIF-FFT algorithm for computing IDFT. Then we will going to consider some of the illustrative example for finding IDFT computation using DIF-FFT algorithm. First, let us consider inverse DFT using Radix2 FFT algorithm. Basically, in the previous sessions, as we learned, our Radix2 FFT algorithm is an efficient way of finding DFT. So, which comes under the category divide and conquer approach for finding DFT calculations. Okay, as DFT is a useful mathematical tool available in our digital signal processing. Using that particular DFT, we can do many of the operations like spectral analysis, frequency transformations, and linear convolution, linear filtering, and many other applications. So we have to find DFT in a faster way. So while looking for the important, efficient, and faster operations or faster algorithms are finding DFT. While considering the classification, we found a divide and conquer approach. There, we took FFT, that is Radix 2 FFT algorithm, Radix 4 FFT algorithm, and then split Radix FFT algorithm. So, this is introduced by Cooley and Turkey in their work. Okay. So in that we considered DIT-FFT algorithm and DIF-FFT algorithm. Basically, we considered and we derived this DIT-FFT algorithm as well as DIF-FFT algorithm for finding DFT. But what exactly we are doing here is we need to find inverse DFT using same Radix 2 FFT algorithm. Basically, in the beginning of this particular module, that is in the first slide or first session of this module, what we considered is frequency domain sampling and reconstruction of time domain samples. That means frequency domain sampling is nothing but finding DFT. Reconstruction of time domain samples are nothing but finding IDFT. Okay, so here we are finding IDFT or we need to find inverse DFT. So for that purpose, we are making use of Radix 2 FFT algorithms. So there are, as we considered the Radix 2 FFT algorithm, there are main two Radix 2 FFT algorithms. One is decimation in time FFT algorithm and decimation in frequency FFT algorithm. So we are making use of these decimation in time FFT as well as decimation in frequency FFT algorithm for computing our inverse discrete Fourier transforms. So now let us have this decimation in frequency FFT algorithm for computing inverse discrete Fourier transforms. What we have, the IDFT equation, x of n is given by 1 over n summation k varying from 0 to n minus 1 x of k into Wn raised to the power of minus Kn, where the value of n is varying from 0 to n minus 1. That means our x of n is having capital N number of samples. Similarly, a DFT x of k is given by summation n varying from 0 to n minus 1 x of n into Wn raised to the power of Kn. Here the value of k is varying from 0 to n minus 1. Again, our x of k is having capital M number of samples. And observe the equations of this DFT as well as IDFT carefully. Only slight difference here. Okay, we are making use of this difference, and we are converting the DIT FFT algorithm for finding DFT to DIF FFT algorithm for finding IDFT. So that we'll going to consider in the next slides, in the upcoming slides. So first let's have the difference between DFT as well as IDFT equation. Okay, as we observed in the previous slide, the in the equations of defining DFT and IDFT, the main difference is factor 1 by n. Okay, that 1 by n factor is multiplied in case of IDFT equation. That means while doing time domain reconstruction from the frequency sample x of k, we are multiplying the equation by the factor. Then the next difference, actually there are only two differences. So next difference is sign of the power of Twiddle factor. In case of equation for defining DFT, the sign of the Twiddle factor is positive. That means Wn raised power of kn. But if you come to the equation for defining IDFT, sign of the Twiddle factor is negative. That is Wn raised power of minus kn. Only these two differences. That is the factor 1 by n and the power of Twiddle factor sign. Okay, so our FFT algorithm for computing DFT can be converted to FFT algorithm for computing the IDFT. With this difference, if we alter these differences in the algorithm, we can make use of same thing to convert for finding IDFT. So now first let's have the steps for converting DIT FFT algorithm for computing DFT to DIF FFT algorithm for computing IDFT. So first what we need to do is we have to take the flow graph. So we have to take the flow graph of DIT FFT algorithm for finding DFT. So first we have to take. Then what we need to do is we have to reverse the direction. Second step is we have to change the sign of the powers of the Twiddle factors WE. Then we have to replace x of n by x of k and x of k by x of n. Then at the end of the flow graph, we have to multiply every sample by the factor 1 by n. So with these 4 steps, we can convert the algorithm, that is decimation in time FFT algorithm, which is responsible for finding DFT, to be algorithm which computes IDFT. So flow graph for this is the DIT FFT algorithm for finding DFT. You can observe here. See, this is taking the samples. It means time domain samples in bit reversal order. Outputs we are obtaining here are in natural order. This is DIT FFT algorithm for finding DFT. According to the steps for conversion, this to DIF FFT algorithm for IDFT computation, as they have told, we have to reverse the direction. Then we have to change the power of Twiddle factors. Then what we have to do? We have to change we have to replace x of n by x of k and x of k by x of n. Then we have to multiply all the samples of output with the factors 1 by n. So next let us have flow graph for DIF FFT algorithm. See, this is DIT FFT algorithm. So this is the DIT FFT algorithm for finding IDFT calculation. See, so this is DIT FFT for finding DFT and this is DIF FFT for finding IDFT. So what are the steps we followed here are, first we have reversed the directions. See, we have reversed the direction. So this is x of n to x of k, but here it is from x of k to x of n. So that is the direction flow we have reversed. Next what we did is we have changed the sign of the powers of the twiddle factor. See here you can observe the signs of the power factors. All are positive here. W8 per 0, W8 per 2, all those things. Here you can observe W8 per 0, W8 per 1, W8 per 2 and W8 per 3. But if we come for our DIF-FFT algorithm for finding IDFT, see here the twiddle factor powers defined are W8 per minus 0, W8 per minus 2, W8 per minus 0, W8 per minus 1, W8 per minus 2 and W8 per minus 3. And what we are considering here is for the value of n, that's capital N is equal to 8. So next step we considered is we have replaced x of n by x of k as well as x of k by x of n, and at the end we are multiplying the output by the factor 1 by n. So here the value of n is 8. So what we are doing is we are multiplying all the samples by 1 by 8. So we will obtain this particular flow graph. So this is the flow graph for finding IDFT using DIF-FFT algorithm for n-point IDFT. So from this flow graph, what we can observe is we will be giving input, that is x of k, in bit reversal order, and we are obtaining the IDFT in natural order. So for the bit reversal frequency samples, we obtain natural order time domain samples. That's it. That too using DIF-FFT algorithm for IDFT computation. So now let's have some of the example to get understand this particular algorithm in better way. Okay. So they have given the DFT as x of k is equal to 4, 1 minus j 2.414, 0, 1 minus j 0.414, 0, 1 plus j 0.414, 0, 1 plus j 2.414, and we have to find our x of n using DIF-FFT algorithm. So to solve this, so it is 8-point samples they have given. So there are 8 samples. And the given sequence or DFT is 4, 1 minus j 2.414, 0, 1 minus j 0.414, 0, 1 plus j 0.414, 0, 1 plus j 2.414. And the twiddle factors and their powers required for this computation of IDFT is W8 power minus 0, that is equal to 1, W8 power minus 1, which is equal to 0.707 plus j 0.707. W8 power minus 2 is j. W8 power minus 3 is minus 0.707 plus j 0.707. So we can have here. So input we are taking in bit reversal order. The DFT x of 0 is 4, x of 4 is 0, x of 2 is 0, x of 6 is 0, x of 1 is 1 minus j 2.414, x of 5 is equal to 1 plus j 0.414, x of 3 is 1 minus j 0.414, x of 7 is 1 plus j 2.414, and output we will be obtaining from this first stage of decimation is 4, 4, 0, 0, 2 minus j2 minus j 2.828, 2 plus j2 and minus j 2.828. So these outputs from the first stage now we will be considering as input to the second stage, and after computing the second stage, we obtain the outputs as 4, 4, 4, 4, 4, 2.828 minus j 2.828 minus j4 minus 2.828 minus j 2.828. So the outputs from the second stage. Now we will be considering it as input to the last stage. So output of the third stage now will be multiplied with the factor 1 by n, that is 1 by 8. After doing this process, what we obtain? The output as x of 0 is equal to 1, x of 1 is equal to 1, x of 2 is equal to 1, x of 3 is equal to 1, x of 4 is equal to 0, x of 5 is equal to 0, x of 6 is equal to 0, and x of 7 is equal to 0. So, the output are the time domain samples of the corresponding or given frequency sample x of k are x of n is equal to 1, 1, 1, 1, 0, 0, 0, and 0. So this is the first illustrative example. So next second we can consider the example as, see here, given x of k is equal to 0, 2 plus j2 minus j4, 2 minus j2, 0, 2 plus j2, j4, 2 minus j2. Here we need to find the IDFT x of n using DIFFT algorithm. So first let us solve this. So given the value of n is equal to 8. So there are 8 samples in the given DFT. And given DFT is x of k is equal to 0, 2 plus j2 minus j4, 2 minus j2, 0, 2 plus j2, j4, 2 minus j2. And the total factors, W8 power minus 0 is 1, W8 power minus 1 is 0.707 plus J 0.707, W8 power minus 2 is plus J, W8 power minus 3 is minus 0.707 plus J 0.707. So, this is the complete flow graph with all the intermediate answers. So, input we are considering in bit reversal order. X of 0 is equal to 0, x of 4 is equal to 0, x of 2 is equal to minus j4, x of 6 is equal to j4, x of 1 is equal to 2 plus j2, x of 5 is equal to 2 plus j2, x of 3 is equal to 2 minus j2, x of 7 is equal to 2 minus j2. Okay. After performing the first stage computation, we obtain the outputs as 0, 0, 0, minus j8, 4 plus j4, 0, 4 minus j4, and 0. And we will be employing this output of the first stage as input to the second stage. And after performing the second stage computation, we obtain the outputs as 0, 8, 0, minus 8, 8, 0, j8, and 0. And now we will be considering these values as input to the third stage. And after obtaining the third stage of output, we will be multiplying all the samples with 1 by 8. So after multiplying 1 by 8 to these outputs, we obtain the outputs x of 0 as 1, x of 1 is equal to 1, x of 2 is equal to minus 1, x of 3 is equal to minus 1, x of 4 is equal to minus 1, x of 5 is equal to 1, x of 6 is equal to 1, and x of 7 is equal to minus 1. So, for the given DFT x of k, the obtained IDFT x of n is equal to 1, 1, minus 1, minus 1, minus 1, 1, 1, and minus 1. So, this is the answer for this second illustrative exam. So now let us consider the another example where the given value of x of k is 0, 2 root 2 into 1 minus j, 0, 0, 0, 0, 0, and 2 root 2 into 1 minus j. And we have to find IDFT x of n using DIFFT algorithm. So again we have to consider length of this sequence, that is n is equal to 8. Given sequence x of k is x of k is equal to 0, 2 root 2 into 1 minus j, 0, 0, 0, 0, 0, 2 root 2 into 1 minus j, W8 power minus 0 is 1, W8 power minus 1 is 0.707 plus j 0.707, W8 power minus 2 is plus j, and W8 power minus 3 is minus 0.707 plus j 0.707. So now let's have this flow graph. So here we can observe the complete flow graph representing input to output along with all the intermediate results here. So before first stage we are taking the input, that is x of k, in bit reversal order. So x of 0 is equal to 0, x of 4 is equal to 0, x of 2 is equal to 0, again x of 6 is equal to 0. Then x of 1 is equal to 2.828 minus j 2.828, x of 5 is equal to 0, x of 3 is equal to 0, x of 7 is equal to 2.828 plus j 2.828. Now we are given the input to this particular DIF-FFT algorithm for computing IDFT in bit reversal order. So after the computation of first stage, we obtain the outputs as 0, 0, 0, 0, 2.828 minus j 2.828, 2.828 minus j 2.828, 2.828 plus j 2.828 minus 2.828 minus j 2.828. Okay, and this output now can be taken as input to the next stage. So, okay, after computing the second stage computation, we obtain the outputs as 0, 0, 0, 0, 5.656, 5.656 minus j 5.656 minus j 5.656 and 0. So now the output of this second stage is considered as input to the next stage. And after computing this third stage of computation, and after multiplying with the factor 1 by n with all the samples, output samples, we obtain the outputs, that is our x of n IDFT as 0.707, 1, 0.707, 0, minus 0.707, minus 1, minus 0.707 and 0. So our value of IDFT x of n for the given x of k is given by x of n, which is equal to 0.707, 1, 0.707, 0, minus 0.707, minus 1, minus 0.707 and 0. So with this we can have what are the outcomes from this particular session. So learning outcomes, we try to find, we are finding, try to explain how to find the inverse DFT using radix to FFT algorithm. Then we considered converting DIT FFT algorithm for computing DFT to DIF FFT algorithm for finding IDFT. Then we considered some of the illustrative examples using DIF FFT algorithm for computing IDFT. So these are the references which you can go through. The book by Prokis and Monolokis in Digital Signal Processing Principles, Algorithms and Applications. The second book we referred is book by Lee Tan and Jean Jian in their book Digital Signal Processing Fundamentals and Applications, and book by Mr. Uday Kumar S in Digital Signal Processing. For the stuffs related to this particular video session, you can access through these links. So with this you can access to the video. With this link you can access to 8th session of PPT of 8th session. With this link you can access to MCQ of the session 8, and with this link you can access to notes of session 8. So this is the LMS team responsible for this session videos or these videos. Okay. Thank you. Thank you very much.